Section: Introduction. In this section, we discuss vision generative models that convert noise into images. When we want to reverse these models using a reference image, we need to find the structured noise that can recreate the original image. For effective inversion, we must ensure two key aspects. The structured noise should generate an image that closely resembles the reference image, and the resulting image should be easily adjustable with new prompts for fine-tuning. Diffusion models, DMs, are currently the leading method for generating images, excelling in sampling from complex distributions. The sampling process is based on a stochastic differential equation, specifically a reverse SDE. Importantly, these models can also invert a given image. Recent improvements in DM inversion have significantly influenced conditional sampling tasks, such as converting strokes to images, editing images, and applying styles. However, DM inversion still faces major challenges regarding the accuracy and ease of editing. The stochastic nature of the process requires precise adjustments to the reverse SDE, which can lead to costly neural function evaluations. If we use a rough approximation, the outputs may not be very accurate, even with deterministic methods. Additionally, non-linearities in the reverse path can cause unwanted deviations, affecting the reconstruction quality. While some methods improve accuracy by optimizing latent variables or prompt embeddings, they often become less efficient, harder to edit, and depend on complex attention mechanisms, making them less practical for real-world applications. To address these issues, we propose a zero-shot conditional sampling algorithm using rectified flows, RFs, which serve as a strong alternative to DMs. Unlike DMs, which rely on a reverse SDE for sampling, RFs utilize an ordinary differential equation, or reverse ODE, which allows for more efficient training and quicker sampling. We create a controlled forward ODE, starting from a given image, to set the initial conditions for the reverse ODE. This reverse ODE is then directed by an optimal controller derived from solving a linear quadratic regulator problem. We demonstrate that the new vector fields we create have a stochastic interpretation with suitable drift and diffusion. We evaluate RF inversion in tasks like stroke-to-image generation and image editing, showing strong qualitative results in other areas, such as cartoonization. Our method significantly enhances photorealism in stroke-to-image generation, outperforming the best existing method by 89% while remaining true to the original stroke. Additionally, we find that RF inversion is 4.7% more faithful and 13.8% more realistic than DM inversion on the LSUN bedroom dataset. We summarize our theoretical and practical contributions as follows. We present an efficient inversion method for RF models that does not require extra training, latent optimization, prompt tuning, or complex attention mechanisms. We develop a new vector field for RF inversion that balances consistency with a potentially corrupted input image and alignment with the true distribution of clean images. We prove that this vector field corresponds to a rectified SDE that balances these competing objectives. We extend our theoretical findings to create a stochastic sampler for RFs and demonstrate the faithfulness and editability of RF inversion across three benchmarks: LSUN bedroom, LSUN church, and SFHQ, focusing on stroke-to-image synthesis and image editing. We also provide extensive qualitative results and conduct large-scale human evaluations to gauge user preferences. Section Summary. In this section, we introduce a zero-shot conditional sampling algorithm using rectified flows, RFs, for efficient image inversion and editing, addressing challenges in faithfulness and editability faced by traditional diffusion models, DMs. Our method significantly enhances photorealism and maintains fidelity to input images, outperforming existing techniques in various benchmarks without the need for additional training or complex processing. Section: Connection between rectified flows and linear quadratic regulator. In this section, we explore the connection between rectified flows and the linear quadratic regulator. We begin with unconditional rectified flows, which allow us to generate images by simulating a vector field initialized with random noise. By reversing this vector field, we can retrieve the original noise sample. Specifically, If we have an image and a corresponding vector field, we can simulate an ordinary differential equation, ODE, to obtain structured noise. If we then apply the reversed vector field to this noise, we can recover the original image. The key implication here is that rectified flows can perfectly invert an image when the vector field is known. If we start with a corrupted image and simulate the reversed vector field, we obtain a noise sample that is consistent with the corrupted image. However, if the image is atypical, the noise sample is likely to be atypical as well. Our aim is to adjust our approach so that we can recover a clean image even from a corrupted one, focusing on generating noise that is more typical. To achieve this, we derive an optimal controller that minimizes energy while transforming any image into a typical noise sample. We consider optimal control in a multidimensional space, where we minimize a cost function related to the control process. The solution to this problem is known as the linear quadratic regulator, LQR, which helps us minimize the transport cost in our system. We have two vector fields, one from the rectified flows that transforms a typical image into typical noise, and another from our optimal control that ensures any image is converted into typical noise. By passing this noise through the rectified flow ODE, we can generate a clean image that aligns with the true distribution. Our controlled ODE balances the need for consistency with the possibly corrupted image and the distribution of clean images. We introduce a parameter that allows us to adjust this balance. When this parameter is set to 1, we follow the optimal control path, ensuring the noise adheres to the desired distribution. Conversely, when set to 0, we revert to the original ODE, which guarantees recovery of the reference image. Additionally, we note that our controlled ODE can be interpreted as a stochastic differential equation, SDE, which is less sensitive to initial conditions. This robustness is beneficial, especially when starting with a corrupted image. As we adjust our parameter, the process can converge towards clean images, allowing us to recover the original image effectively. Section Summary. In this section, we explore how rectified flows, RFs, can accurately invert images, even when starting from corrupted ones, by employing an optimal control framework akin to the linear quadratic regulator, LQR, problem. We introduce a controlled ODE that balances consistency with the corrupted image and adherence to a typical noise distribution, allowing for effective image editing while maintaining inversion accuracy. Section: Controlled rectified flows as stochastic differential equations. In this section, we derive a stochastic differential equation, SDE, formulation for our controlled ordinary differential equation, ODE. We start with a d-dimensional Brownian motion in a specific probability space and consider a fixed time interval. The controlled ODE describes how the density evolves, which is similar to the density evolution of the corresponding SDE. When the controller parameter is set to 0, we find that the SDE aligns with standard rectified flows, enhancing the accuracy of the initial image. If we set the parameter to 1, the SDE addresses the linear quadratic regulator, LQR, problem, guiding us toward a specific terminal state, which improves the quality of the generated samples. We choose a time close to 1 to maintain numerical stability and avoid boundary issues, resulting in our final sample being effectively the same as the desired output. We also compare our approach to diffusion models, DMs, which typically use the Ornstein-Uhlenbeck process. Our method, based on rectified flows, leads to a different ODE and SDE. We formalize this relationship, showing that the marginal distribution of our ODE matches that of an SDE with suitable drift and diffusion terms. We demonstrate that the stationary distribution of our SDE approaches a standard Gaussian distribution as time progresses. Next, we develop a reverse process using both ODEs and SDEs to transition from noise back to images. We start with structured noise and create a controlled ODE that uses a reference image for guidance. The controller parameter helps balance the faithfulness and editability of the image. By solving a modified LQR problem, we steer the samples toward the reference image, reducing reconstruction errors compared to standard reverse ODEs. Finally, we present the stochastic equivalent of our controlled reverse ODE. We initialize with structured noise and a reference image, ensuring numerical stability by terminating the process slightly before 1. The density evolution of the controlled ode matches that of the corresponding SDE. When the controller parameter is 0, we obtain a stochastic sampler for the pre-trained model, allowing for efficient zero-shot inversion and editing without additional training. When the parameter is 1, the SDE simplifies to recover the reference image exactly. Our analysis also accommodates time-varying parameters, which is beneficial for editing as it allows for initial movement toward the reference image before gradually enforcing edits.